Hello, calculus fans. All right, we're going to start talking about sequences. What is a sequence? It's just a list of numbers. A1, A2, A3, up through AN, just a bunch of numbers. So we call A1 the first term, A2 is the second term. So we have terms of a sequence, is what we'll call them. Now we're only going to deal with infinite sequences, sequences that go on forever. Now for each positive integer n, there is a corresponding a sub n. So we could, and really this is how we should think of it, a sequence is a function whose domain is the positive integers. So you plug in a positive integer, and then I give you a real number that comes out. All right, notation. So our sequence, A1, A2, A3, we can also write it with these braces where we just describe the nth term. Or sometimes you'll see it written this way with a n equals 1 going to infinity. Sometimes we can describe a sequence with a formula. So for instance, if I gave you this sequence, 2/3, 3/5, 4/7, 5/9, 6/11, and so on, you could actually describe this with a nice little formula. A sub n is equal to n plus 1 over 2n plus 1. See what happens when you plug in values of n. Like if you plug in a 3 for n, you'll get 4/7, which is the third term of the sequence. If you plug in a 5, you would get 6/11, the fifth term. So that formula describes the terms of the sequence. Now, it's not always possible to do this kind of thing. I've got a sequence where there is no formula that describes the nth term. Like this. 3, 1, 4, 1, 5, 9, 2, 6, 5. These are the digits in the decimal expansion of pi. There's no formula where you can just plug in something and get the nth term of the decimal expansion of pi. All right, so let's take this as an example. Let's try to write a formula for the general term of this sequence. 5/6, -7/36, 9/216, and so on. So one thing to notice is that the terms alternate in sign. They go from positive to negative, back to positive. The denominators are powers of 6. So the first one is 6 to the first power, 36 is 6 squared, 216 is 6 cubed, and so on. And then the numerators, they go up by 2 each time. So here's one possible answer. So going up by 2 means we need an expression that looks something like this, the 2n plus 3. Notice that if I plug in an n equals 1, I'll get 5. If I plug in n equals 2, I'll get 7. Then the 6 to the n in the denominator handles the powers of 6 that are in the denominators of the terms. And then finally, -1 to the n plus 1, that gets you an alternating sign. Depending on if that exponent is odd or even, you'll get out either a positive 1 or a negative 1, and that's generally how you get alternating signs. Okay, so let's look at a completely different sequence. This sequence, a sub n equals 2n over n plus 1. Those have terms which appear to get close to 2. Plug in a big number for n, and you're going to get something that's close to 2. So you should try it. Plug in some values for n, making sure that the things that you are plugging in are only positive integers. The bigger the value that we plug in for n, the closer that a sub n gets to 2. In fact, with a little algebra, we can see that a sub n equals 2 minus 2 over n plus 1. So if we look at the difference between 2 and a sub n, the difference is going to be 2 over n plus 1. And that we can make as small as we like. So what we'll write is that the limit of a sub n, which is the limit of 2n over n plus 1, and this is a limit as n approaches infinity, is equal to 2. So we'll use this notation, limit as n goes to infinity of a sub n equals L. That means the terms of the sequence approach L as n gets large. So we'll take this as a definition of a limit of sequence. A sequence a sub n has the limit L if we can make the terms a sub n as close to L as we like by taking n sufficiently large. So we're going to write the limit as n goes to infinity of a sub n equals to L. If that limit exists, then we're going to say that the sequence converges, or we'll say that it is convergent. Otherwise, we say that the sequence diverges, or is divergent. Now really, there's very little difference between the definition of a convergent sequence and the limit to infinity function of a real variable. And in fact, the nice thing is that we have a theorem that relates the two, and this is going to be very useful later on. So the theorem says that if you have a function of a real variable, and that function has a limit L as you go out to infinity, and then when you plug in some positive integer, you get this sequence, then the limit of that sequence is also equal to L. All right, the last thing we want to talk about is that we showed this fact in calculus 1, that the limit as x approaches infinity of 1 over x to the r is equal to 0, at least when r is positive. Now if we combine this fact and the previous theorem about matching up functions and sequences, we have that the limit as n goes to infinity of 1 over n to the r is equal to 0 when r is positive. I should note that if a sub n becomes large as n becomes large, then we'll write the limit as n goes to infinity of a sub n is equal to infinity. And in this case, we would say that the sequence a sub n is a divergent sequence, but it diverges in a particular way. And we would say that a sub n diverges to infinity. So that would happen in the case of this sequence if r was, say, less than 0. Okay, that's all for now.